Hello and good morning. Let's try to set up this correctly. Yep. Today we're going to talk about a very important topic that most universities, I think, do not teach like directly. They would basically give hints, but never teach like to the point. So it's basically turning architectural drawings into structural drawings. So let's share the screen with the iPad via screen mirroring. 2 seconds. Right. So by the end of this session, we will be able to basically understand the basic principles of transferring architectural drawings to structural statical system. A statical system is a system that doesn't move, or so they say. Let's zoom. Okay, so we're going to talk about like a building as a whole. Then we're going to talk about each individual member and its place in the chain. So first, we're going to have the general rules and guidelines that must be followed when deciding on a structural system. Yeah, as I just said, this will be separated for simplicity for each member and the building as a whole. We're going to start though regarding the regulations regarding the structure as a whole, like the full thing, from foundations till the top floor. This is basically as a disclaimer. This is for villas, like small houses, small lower, like maybe even high-rise buildings, but not too high, something like 5 floors or maybe 8 floors, like a residential type. Yeah, this is very residential heavy. The spans must not exceed 4 meters to 6 meters. Yeah, maximum 8 meters, only if the other direction is shorter. Okay, what we mean by that is basically you're gonna have something like this. For example, 8 meters, but the shorter direction is probably 4 meters. That passes as an okay slab, you know, like an okay plan. Yeah, because bigger than that, you're going to think outside of the box, basically, and use structural configurations that are not simple, not as simple as this, basically. Number 2, try to have frames in both directions of the house to resist horizontal forces. Let's draw this. So basically number 2 here, like have columns like this and have columns like that, basically. That's what I'm trying to mean here. Like make sure that you have systems that are basically resisting loads that's coming from this side and systems that are resisting loads coming from that side all the time. So you have something to resist wind load or earthquake load or whatever, you know, even for minimums. Avoid having congestions of columns in one area so that their foundations do not become combined. Yeah, that's a thing. Yeah, number 3. You don't want to have your columns like this, that column and the other column, for example, like this, like my drawing. Well, their foundation, like below ground, would be something like this, and they would intersect basically. Then you have to combine them. Too costly and could be avoided with better configuration understanding. In this, the art of statical systems is visual, you know, it's just visual. You have to visualize. Yeah, a column here, beam will connect here, a main beam connects there, a secondary beam goes here, and you try multiple times until you land something solid. Number 4, try to make the structure as symmetrical as possible. This is basically important to make the structure as symmetrical as possible. If that's your structure, for example, symmetrical, then you have columns like here, 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 here. Basically your center and one in the middle, just for good measures. You want your center of mass to coincide, be at the same place of your center of gravity. Yeah. If you have a center, if your center of mass and center of gravity defer, you're going to have twist in the building. When loads are applied, you're going to have twist on the members, and you know, especially concrete members, even steel sometimes, they don't like twist, they don't like torque. So you have to basically mitigate for that. Number 5, in case of large areas, make sure to have multiple load paths to mitigate any local failure. Yes, you have to have multiple load paths in a building to mitigate any local failure, because what we don't want is one beam failing, one secondary beam failing, for example, and the whole building collapsing, like something we call a pancake collapse, or one column. If we lose, let's see, for example, what do I mean by that? Let's put it here. So if I had a building like this, for example, yeah, just beams basically and columns. If you lose this, you're going to lose this. This will become a cantilever. This will become a cantilever. They will collapse. You lose the whole system here. You lose this whole area. Having multiple load systems means maybe a secondary beam here, connected to probably another column in the middle. You try to reduce that as much as possible. I mean, this is not going to fail per se, you know, just saying the case of failure, you have to have multiple force systems. If you lose one member of bracing, you make sure that there are other systems in the building that could resist wind load, like shear walls, for example. We're going to talk about that in detail. But yeah, take it for what it's worth right now. Yep. 6, in case of adding new construction to old construction, it is key to avoid using the old concrete frames to carry the new loads and to try to use the newer frames instead, if it wouldn't cost much. Yeah, what happens when you build a building, for example, this is old. Old is usually hatched, and this is new. Yeah. Let's say, for the sake of argument, we have columns here from the old building. Some people will just put columns here. Some people will put columns here and connect these columns with beams and use the old column, maybe even strengthening it. And that's cool. That's perfect. But I don't prefer that. I don't prefer that. Old and new never happen to be, you know, nicely correlated. It's better to use newer columns here, newer columns here. Let's change the color. Newer columns here, newer columns here, here. And for their foundation, we're breaking rule number 3, right? You're thinking, no, we're not breaking rule number 3. We're good here. We're not, because I could place this column anywhere I want and just like cantilever the rest. 7, expansion joints must be added every 40 meters of the building or less. So every 40 meters of the building, you have to have an expansion joint. Let's see, for example, this and that. Here, we could put an expansion joint, because concrete shrinks and, you know, stretches. So we make sure that this is mastic, something called mastic. Yep. Note that these are not the only ones, but you must start somewhere. Yeah, I have to talk some philosophy here. Basically, when you're designing a building, you have no idea what you're doing, right? You're thinking, like, what do I do now? Okay, I have this architectural system and I need to turn it into a structural system. These are basically guidelines to make you start. You could break any of these rules, by the way. The price of breaking rules, these are not rules, recommendations. Yeah, you have to compensate. You have to have this, for example, a combined footing system. You have to compensate with cost. You're going to have old and new. You're going to have cracking, and you're going to have to mitigate for that with a lot of things you could do. But yeah, expansion joints, again, cracking, and maybe even one of them will go over the other. Okay, let's see. Rules regarding columns. Rules regarding columns. Let's come closer. Okay. Rules regarding columns. Avoid having congestion of columns in one area so that their foundation doesn't become combined. We said this بالإضافة basically. Columns change shape or orientation interstory on a beam. That's an important rule actually. Columns change shape or orientation interstory on a beam. Key. If you want to change, for example, let's see number 2. If in floor one you have this shape of a column, yeah, in floor 1, and on floor 2 you want to turn this into that. You want to turn the column to hide it inside a wall or something for aesthetics. What happens is you have to do this move on a beam. So the beam on the lower floor now, yeah, will be basically, you do that on a beam. Then the newer column will start like this, basically. Like center, of course. Yep. So how do they, this is gonna be the old one in blue. And this is and the green will be the new one. Yeah. This is in the basically first floor. This is in the second. This is for turned columns, yeah, by the way. For planted columns, we're going to study planted columns. This is number 2. This is for turned, planted. Sometimes you have architectural regulations where you could place beams, place columns on the periphery of the building, but that's not allowed through regulations to be on the periphery of the building on the second floor. So basically you're going to lose the columns that you placed on the corners of the building in the first floor. You know, they should be connected, ideally. Ideally you want a column like that and a column like that on top of it, right? And this is like a story, my finger, yeah? But sometimes, like I said, at the periphery of the building, you have this, and then you have a column here starting on the new periphery of the second floor. Now you have a gap between that column and this column. What do? Okay, you could find a column that's inside and call it a day, right? But what if I don't have something here? There is a solution. It's called the planted column or floating column. Very common practice in many countries, but research on it is very little, and it has problems with creep, which is the sustained load over time, lecture 1. Yeah, so a planted column will be something like this. Yeah, you have this structural system. For example, and this is an example of it. This is not the only example. Like this is floor 1. Yeah, so floor 1 has this beams and columns, a system basically of beams and columns. What if I wanted to plant a column here on another floor? I'll just connect these with a beam, and basically my column will start from here. So in cross section, it will look like something like this. This is the column. Another column. Yeah, you have this column like that. You try your best for it not to be center, because moment here is max. You try to make it here, somewhere here, like where the shear is not maximum and the moment is not maximum. You try to basically, help your case. And columns changing sections. Yeah, same thing. You do all of these on a beam. See, that's a beam. That's a beam. That's a beam. If you want to do anything with the column, you have to do it on a beam because there's lots of steel that's going to change orientation and be tied differently and all that shenanigans. So you have to basically like contend with the fact that you're going to do it on a beam regardless of the consequences. Columns changing sections. Yeah, sometimes you start with a circular column, and you want to make a rectangular column on top, or the opposite. Basically, you do that on a beam. I don't have to draw this self-explanatory. So I had something else on turned columns, yeah. So something else on turned columns. I'll put it here. Types of turned columns. We have this, the cross, and we have the cross, and we have the T basically. We have the T and we have the L. We have the L-shaped. This is basically these are the red are new or the other story. So basically, like we see, this is strongest, second strongest, weakest. Cool. Yeah, perfect. Yeah, let's see, what else did I talk about? So let's, yeah, so we said every corner will, yeah, every corner rules now, number 3. Every corner of the building must have a column. Good place to place columns on the corners. Like we said, the periphery of the building, it's there. Yeah, it's there. Just zoom out. If possible, every corner, you said that, okay. Sorry, distance between columns should be 3 meters or 6 meters, just not exceed 8 meters. Again, the same rules not before, yeah? Every possible corner of the room must have a column. Okay, this is a rule to be broken, but yeah, like I said, like if you want your room separated with columns, if you can. The minimum column must be 25 centimeter by 25. Code would say 20 by 20, but 20 by 20 will never get you so far. It will fail always. 25, maybe you have a chance. No columns are intersecting windows. Yeah, you have to pay attention to your architectural drawings. You have no idea how many times there's a structural mistake where the structural engineer will just delete all the architectural installments on AutoCAD. Then basically what he does is place his columns and everything. Then like maybe sometimes months in, he would like submit his stuff and they realize there's a window where the column should be. That's a problem because you maybe began constructing even. That's not something fun to be dealing with. So pay attention to your layers. You don't just delete everything the architect drew. I would recommend deleting at some point so you have space to work your magic, but at least have them as a filter. And whenever you finish your structural drawings, you turn on the filter of windows, the filter of doors. Like make that a conscious effort and you're not gonna make mistakes. And trust me, many people make mistakes. Everybody makes these mistakes anyway. You try your best to have the same stiffness in the planes so you don't create torsion or create too much torsion because torsion is gonna be there in small amounts anyway. You want your center of mass and center of rigidity to not have too much eccentricity. We talked about this basically. Let's see, let's imagine this basically, yeah. Columns, my columns here are X. Number 8. Yeah. So basically, I want my stiffnesses of the columns. For example, we always talk about columns in terms of something we call stiffness K. Okay, so one column would be K and the other column would be 2K, one other column would be 3K. I make sure through my calculations that this equals this, equals this, equals this in terms of stiffness. I want 4K here, 4K here, 4K here, 4K here, for example. So my center of mass and center of rigidity, COM and COR, coincide. Yep. If I don't have that, then I'm going to have some eccentricity where the building will be like this. Center of mass is here and center of rigidity is here, and we have something called eccentricity. Distance in meters. There's discrepancies between them, and that's not fun. That's basically torsion on the building, basically. Torque. Okay, number 9. It's better to hide columns inside the wall if possible. Corners of staircases are excellent places for columns. Yeah. Yeah, so we have a formula for stiffness. Let's put it here. So K equals 12 EI over L cubed. So it's a very simple formula. It's a very simple check to check the rigidity and center of mass. Center of mass is basically where your force vector will apply. Yeah, like usually if you have the same stiffnesses, then you have the same mass everywhere, kind of. Yeah. Yep. So we have rules regarding beams. Rules regarding beams. Never load a secondary beam on a primary beam to avoid local failure loops. Okay, what I mean by that, you have two types of beams, secondary and primary. Primary, part of the main frame. Secondary, it divides your slabs, basically. It's something that divides your slabs and where you could place walls as well. So if you have like this plan here, you have this plan here. Excuse my sketching, I'm not the world's best sketcher. Let's see, that's a secondary beam, okay? And we have a secondary beam loaded on top of it. So this is loaded on the other color. This is loaded on this, and this is loaded on here, and here, and this is loaded on this. What happens here is a problem. If this beam fails, this will fail, this will fail. And we don't want that. We don't want everything to fail at once. We don't have a loop. We don't want to have a loop. Like some people will put something like secondary beam, loaded on a secondary beam, loaded on a secondary beam, loaded on a secondary beam. Yeah, and maybe be hooked by primary somehow. What happens is if this fails, this fails, this fails, this fails, everybody's carrying the other, and none of them is designed to take the load of two beams. So they just collapse. So you don't load a secondary beam on a secondary beam. Forget it. Do something else. That's a rule, actually. That's not regulations. Not recommendations. That's a rule. Never load a secondary beam on a secondary beam. Every wall must have beam or additional steel under it. Yeah, the problem is with deflection. Yeah, you want something to resist that deflection, basically, and you resist the cracking this is going to cause from bending. So basically, you're going to have a wall, basically. For example, a beam. You're going to build a wall on top of it. Amazing sketching, right? Yeah, beam, wall, correct. If you don't have a beam, Then you make sure when you're designing your slab, imagine this is your slab, and you have a wall here. This is top view. You have a wall here that you're going to indicate inside your plan that you're going to have additional steel. 3, 5, 12, for example. Here, just 3, 5, 12. That's what I mean. Yes. So ducts are preferred to go under the beam. If holes have to be made, then it's preferred to make them at 1/3 of the beam span where the shear moment are not their maximums. What do we mean by that? You know, services. You have services in the buildings that are going to cross beams, for example, and maybe you don't want to put false ceiling and hide everything. So what you have to do is basically you have this beam, right? We have to theoretically explain it. This is a load WX per meter. Yeah, what happens is we're gonna have the Vx shear would be something like this. Yeah, and you have your moment diagram. Like this. Yeah, so you have maximum here, max, and max shear here. Maximum is here. So where not to put your holes here and here. So let's imagine a beam. Let's imagine a beam right now. That's a beam, for example. This is columns for the beam. Just for the sake of argument, yeah. You want your holes to be at 1/3 of the span, somewhere here. Yeah, from here or from here. 1/3 of the span, because you have maximum in the middle, so you don't want to reduce your section by cutting a hole, and you don't want to cut in the beginning, so you don't reduce the shear resistance. So unless you calculate and mitigate, you want to break these rules, you have to mitigate. It's possible. I'm not saying it's not. I've seen it happen, but you know, you have to be careful. So as a general rule, if you're starting to put together the plan, then just do it correctly from the start. For every 4 meters of Hordy, which is rib slab, we must have an X rib. Yeah, basically. This is just like a rule I found fun. So if your span exceeds 4 meters in a ribbed slab, so you have to have an X rib. Like if that's the beam, main beam, and you have these Hordy beams, ribbed slab for longer spans. We're going to study them very well in the future. Let's imagine that span is more than 4 meters. Just make them longer. We're going to have an X rib here. Then we're going to have another set of them. Usually, you wouldn't have them if the span is less than 4 meters. Basically, these ribs will connect together, and that's that. But yeah, beams are preferred to be the same width of the wall, again, for aesthetics reasons. You don't want to see things sticking out of the wall, basically, because they're, you know, are dropping from the wall and stuff like that. Unless you have like a false ceiling, then that's fine. Rules regarding slabs. In the case, rules regarding slabs. In the case of bathrooms, the slab is moved downward for 10 to 15 centimeters for piping. So whatever you do, this is like the floor beam, for example. Yeah, and this is gonna be your slab. For example, just for the sake of argument, yeah? And you have a floor beam here. This is the shower. Very nice, right? This is, a happy human being with no hair, like me. So you have this 15 centimeter, 10 to 15 centimeter drop. There is a detail for it. I'm going to show it when I'm talking about slabs, how to change the steel from here to here, from here to here, basically. Yep. In flat slabs, it is key to check for punching shear and mitigate if needed, either with the crown or increasing the thickness of the slab. So basically, if you have a ribbed slab, flat slab. Flat slabs we're going to study in depth, but it's beamless slabs. So it's going to be this column, 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 for example. Yep. You have to mitigate using something we call a drop panel, which is this concrete drop panel, or you have to mitigate with additional steel on the corners. Let's take a section here, section elevation, yeah? So if we have this column head, we're gonna have steel all over here. That's a way of doing it as well. Just thought about it, yeah? Because if your shear capacity is exceeded, then you're gonna have punching shear. Punching shear is basically, it's basically the shear that if you take a pen and stab a paper, it would rip it. That's kind of punching shear, like that, like that. Okay. In the case of openings inside the slab, you have to mitigate that by adding additional steel 45 degrees. Yet in the case of rib slab, you might have to add additional rib in that area to account for the weakness created by the duct gap. Sometimes we have services passing through the building, like from the ceiling, down. Like you have this hole on top, and you make the hole in an existing slab, or you design it like that. Yeah, if it's an existing slab, it needs the calculations. If it's not, we could mitigate it through design. So if that's basically, let's imagine a big slab, solid, this is like fixed. Yeah, and we want to make a hole here. Yeah, we have to mitigate this by putting corner bars all over here. Yep. To mitigate. Sorry about that. Yeah. So, yeah, cantilever slabs are not to extend more than 1 meter. Otherwise, they have to be supported by cantilever beams. What's a cantilever slab? It's fixed with one end. Yeah, it's fixed from here and free here. If this exceeds free. So yeah, we have to basically put cantilever beams if this exceeds 4 meters. Sorry, 1 meter. Yeah, the phone is distracting, wasn't it? Yeah, threw me off. So yeah, this is a cantilever slabs. If you want to add a couple of them, cantilever beams to support the cantilever slab. Now we're going to talk about rules regarding foundations. Yeah, rules. regarding foundations. To avoid differential settlement, we use trap beams or tie beams. So what happens is when you're dealing with soils, it's a non-homogeneous material. So basically some places will have more of something than the other. So what happens is this could go down more than that when you apply weight. Like if you're walking on a beach, you're kind of pressing the ground, yeah? You don't press the ground evenly with every step. And the same thing happens with foundations. When you place it on a soil, what happens is it displaces the soil differently. How do we mitigate that? We use something called a trap beam, shaddat. So this is a foundation, that's a column, that's a foundation, that's a column. We use something we call a trap beam, designed to take the moment required from the settlement. Yep, trap beam. Or tie beam. Ground beams must only carry the slab of the ground floor, and it's important not to confuse it with trap beams. Yeah, this is very important. So basically, what's the difference between a trap beam and ground beam? Basically, a trap beam, it's basically on the level. So this is the ground beam. That's the foundation. That's the column. Yeah, it starts from here. See, it carries the first floor, basically, or what you call the ground floor. Soil. This is the finished floor level. But with ground beams, it's different. Here is the ground beam. Sorry, the strap beam, the tie beam. Cool. Neighboring edge columns must be strapped to more stable footings. Yeah, sometimes you see it. Sometimes you have a neighbor, yeah, that's your neighbor. And they have their edge of the building here. This is the line dividing you from your neighbor, you. You want to place a column here so you could benefit from the whole area. So you place a column here, and he has a column here. What do you do, guys, both of you? Your foundation, yeah, your foundation would be something like this now, right? And this foundation will be something like that. What you do is now you actually put a strap beam and connect it to a more stable footing. Yeah, to a more stable footing, basically. To pull it, basically, to put it in place. This is called a neighbors cannot spell today situation. Very common in Kuwait, by the way. Very, very common in Kuwait. More than you think. So now we're going to take some examples of like turning architectural drawings to structural drawings. This is the one floor villa. Yeah. So we could say, like, what did we say for, let's start with columns. First, you delete all of these things, but you keep them in what? You keep them in a layer. Yep. So it could easily be said like column here, column here, column here. Like definitely column here, definitely column here. Let's put it in red, sorry. Column here, column here, column here. Maybe column here for the thing, column somewhere here, column somewhere here, somewhere here, somewhere here as well, somewhere here, somewhere here. The edges of staircases, we said, remember? Somewhere here, here as well, maybe this corner, maybe this the other corner. Cool, this corner as well. Here it's important. Here as well. Maybe now I'm thinking maybe even delete these and put some here instead for the staircase. Okay, let's compare. Like, what did we use here? As we could see, and now basically we're going to have the beams being these, basically beam like this, beam like that, beam like this. I mean, if we fix the drawing, it wouldn't be like that. So if one is here, then the other is here. Why is it saying blue and it's red? Anyways, this beam, 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 another beam. You get the gist, yeah? Beam. Pay attention, there is a window here. There's no column, so we're correct. That's the final result. We see how we put them. We put additional ones here as well. Well, since this is open, we don't need these beams. I realize this is open, so no beams here. But yeah, if it was closed, there's a roof, then you'd have to put these beams, but not here. In this case, it looks to me as it's open. Yeah. How about this one? How about this one? Well, same. I mean, nothing too complicated. Let's put it that way. Yeah, let's put it that way. Zoom out. We have two floors, right? Here we have two floors. That's the main difference. We have two floors. So same, we're going to take corners. But here, notice that we have a window here. So our column will be something here in this orientation, like this. Here, the corners of staircases. Yeah. So see when I say two different resisting systems. Here as well. Here as well. Here as well. This is basically sky, open, the sky, here, here, here. Maybe here. Same thing happens on the other floor. You try to copy these that we put on the other floor, and if there is any discrepancies or problems, you try to fix them on the two floors. So what happens is you'll take this drawing, yeah, and put it, this drawing basically, and put it on top of this one. And you're gonna have places where your columns are for the second floor. Then if you need more, you add more. If you use the planted column, for example, maybe you need less. If you need less, then that's fine. You basically don't extend the column from the first floor when you're building it. So it's cool, but looks like they're very symmetrical. Yeah, very symmetrical. They look very symmetrical. Yeah, but there's something interesting. I did like solve it here. As we see, we have a column here, a column here, 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 here. And I divided everything here, 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 here. Yeah, there's a mistake here somewhere, yeah. This is basically not preferred very much. Secondary, carrying a secondary. That is not my work, but this is a loop. Cantilever. And we have this basically as an exercise, like if you had an observation deck without a structural system, what do you do if you have a shaft and then suspended deck, for example? You remember the one from last example? Like this is basically a core. Solve it. So you come up with something like this. This is the core. You extend cantilevers, and you put columns like that as wind posts. That's how we solved it. And everything is good and merry. Thank you very much for watching, and I hope this was okay enough